So when we're dealing with alternating series, we have a little bit extra that we have to determine with convergence. Not just yes or no, does an alternating series converge, but what type of convergence does it have? Okay, if an alternating series converges, it can converge absolutely or it can converge conditionally. All right. So one thing I want to point out to help this make sense is up at the top of these notes, I used a sub n to represent just the part of the series that did not include the -1 to the n plus 1, so kind of the function rule without the alternating piece. But down here, a sub n is referencing the entire alternating series, so it includes whatever is the alternating piece, -1 to a power, or cosine of pi n or something like that. Okay, so for absolute convergence, we have to have a series where the positive or the absolute value of that series also converges. In other words, if we take off the piece that alternates, does it still converge? If the answer is yes, then we have absolute convergence, okay? A quick example of that would be -1 to the nth times 1 over n squared, okay? If I do the absolute value of this entire series, I have 1 over n squared, which we know converges. That's a p series, and we know it converges, so therefore this series converges absolutely, okay? Now, if the alternating series, remember a sub n has the negative or the alternating piece in it, if the alternating series converges, but the absolute value of that series, or in other words, the positive part does not converge, then the series only converges conditionally. So a quick example of this would be -1 to the n times 1 over n. The absolute value of this is the harmonic series. The harmonic series we know diverges. So without this -1 to a power, this series would not converge, meaning that this series only converges conditionally, okay? And then if it diverges, if the alternating series diverges, then it doesn't really matter. Now, frequently with alternating series, you are going to use the absolute ratio test. Not always, not 100% of the time, but it does show up probably more often than a lot of the other tests, okay? So it's unlikely that you're going to use the like the integral test, because we're not integrating -1 to a power times something, okay? And absolute ratio test, this is written a little bit different than it was in 9.4. In 9.4, the absolute value bars were around the entire thing. That's not any different, okay? So you can just put absolute value bars around the entire thing instead of numerator and denominator separately, okay? Algebraically, those are equivalent. All right, now with the absolute ratio test, if the absolute value part here is less than 1, remember, let me back up. If the limit is of the ratio of the next term over the current term is less than 1, remember that we converge, and then if it's greater than 1, diverge, and equal to 1, inconclusive. So that is the same thing. But because we put the absolute value bars around the ratio test, then if this limit is less than 1, then we do have absolute convergence, okay? With some of the other tests, you might have to, like if you use the alternating series test to determine if something converges or not, then if you get that it does converge, you would then have to check, okay, now which type of convergence, and you might have to perform a second test to determine absolute or conditional, okay? Let's do a few examples, and, well, hold on. Oh, there we go. Okay. All right, so for this first one, we've got -1 to the n minus 1th, and then times n over n squared plus 1. So I'm really looking at just this n over n squared plus 1 part first. And I am not going to use the absolute ratio test here because this is rational, and I already know that I would get an inconclusive result if I use the ratio test, because I would just end up with 1 as my limit. So, and you're welcome to go through and try that if you would like, but because this is rational, I'm going to use a comparison after I've determined that it converges with the alternating series test, okay? So we're going to start by showing that the limit at infinity of just this part, the non-negative part or non-alternating part, is equal to 0, okay? And if you want to use L'Hopital, you can, or If there's a higher degree in the denominator, then your horizontal asymptote is always 0. All right, so the limit is 0, and then I also want to show that it's decreasing. Again, because this is rational, I'm going to use the derivative to show that this is decreasing. I'm going to show that f prime is less than 0, and I'll go ahead and write that. We're going to show that f prime is less than 0. And I'm not saying this is the only way to do this, but this is just so you can see several examples with different things. This is what I'm using, okay? So let's go ahead and do the derivative of this part. And remember, with the alternating series test, we're only looking at the positive part, not the alternating part. Okay. So the derivative would be n squared plus 1 times 1 minus n times 2n all over n squared plus 1 squared, which is equal to, this is n squared minus 2n squared, and then plus 1. So we have 1 minus n squared over n squared plus 1 squared. And this, since the denominator is always positive, this has to be less than 0 for n greater than 1. Okay, as soon as n gets bigger than 1, then we start subtracting a bigger number than 1, so we have a negative. Okay, so it is decreasing, meaning that, or you could do the n plus 1th term is less than n, that would also, or the nth term, that would also show decreasing. Either way, we have convergence based on those two things. So therefore, it does converge. Now we need to determine what type of convergence. So we want to look to see, does it converge absolutely or conditionally? In this case, I'm again going to ignore the alternating part and just look at this because I want to know, does the absolute value of this series converge, okay? Or does n over n squared plus 1 converge? All right, at this point, you probably know where this is going because we've seen similar to this quite a bit. I'm going to use the limit comparison test to 1 over n. So limit as n approaches infinity of n over n squared plus 1, and then divided by 1 over n is the same thing as times n over 1, and then this ends up being the limit as n approaches infinity, n squared over n squared plus 1, which is 1. Whoops. Run out of room there. So, which is equal to 1. Limit comparison says if the limit exists, which 1 does exist, then this function, our function, our absolute value function, has the same behavior as 1 over n, which diverges, okay? So therefore, the absolute value of this diverges and the whole thing converges conditionally, okay? So the series converges conditionally. All right, if you would like, go ahead and pause it and try the next couple and then play or resume and see if we did it the same way, okay? So for this next one, I've got sine of k over k squared, and sine of k is going to be the alternating part. Now, it's not just jumping between negative and positive 1, because sine of 1 is not 1 or negative 1, sine of 2, etc. We don't have a pi over 2 or anything times there, but I do know that sine of k is going to oscillate between negative and positive 1. Okay, so what I'm going to do is I am going to take the absolute value of the sine k part and then show that the, oh, hold on, move. Well, okay, sorry, a little glitchy. And I'm going to show that what the absolute value, series does. Okay, so because of sine's limitations, then we can say that the absolute value of, looks like sync, sine k over k squared has to be less than or equal to 1 over k squared. Again, because sine has to be between negative 1 and positive 1, this is limited by 1, okay? So I know that this is true, meaning that I could use the direct comparison test. So I can say by direct comparison, the series will converge, Okay, so again, I know that this is bounded by 1 over k squared. 1 over k squared is a p-series, and it is a p-series with p equal to 2, which does converge. So since this is less than or equal to 1 over k squared, this series does converge, and it converges absolutely because this is with the absolute value bars on there. I could show this without the absolute value bars, and then I would have to do something else to check the absolute value part, but it actually works with the absolute value bars, so therefore we have absolute convergence. Okay? And then for this last one, this is actually a geometric series. I am going to write it a little bit differently just so we can look at it in that alternating form. So from 1 to infinity, we could write this as -1 to the nth times 5 over 4 to the n. And now, if that helps it look a little bit more alternating, then that is totally fine. Either way, we have a geometric series, and our ratio, or the absolute value of our ratio, if we use this one, is not less than 1. Okay, so this is geometric with absolute value of r being absolute value of -5/4, which is greater than 1. Therefore, this one diverges. Okay? All right, so again, the types of convergence, really we say if we ignore the alternating piece, does the series still converge? And if so, then it would be absolute convergence. If it requires that -1 piece or the alternating piece in order for the series to converge, then we say it converges conditionally.